Hello everyone, this is Sundar Atre and we will go over lecture 19. So this is the first of the lectures in module 3 focusing on metals used in additive manufacturing. Here are some examples of processes based on a powder bed method using an electron beam energy source for fusion, a blown powder method combined with lasers for fusing powders. Here's an example of different kinds of powder attributes. When you look at the overall map of materials used in manufacturing, you will see that the metals are dominated by a large number of alloys given in these categories. Steels followed by aluminum alloys, copper alloys, zinc alloys, which are low melting alloys. Lead falls into that category as well. Then nickel, magnesium, titanium, and then the precious metals. Okay, so these are the relative consumptions and how they stack up relative to polymers, relative to some of the common construction materials, and some natural materials, including wood. Let us focus on metals in this lecture. In terms of additive manufacturing processes involving metals, you can use powders, wires, foils as possible starting materials or building blocks to add together to create a shape. While all these options exist, additive manufacturing of metals is dominated by the use of powders. The key focus of this class is to realize that there are a whole range of variations of powder attributes. In this case, in terms of shapes, ranging from spherical to agglomerated and a lot of different things in between. So shape is an attribute that needs to be understood. The size needs to be understood as well, and it's the packing density of the material, the surface area, which is related to the particle size, but is also related to the particle shape. There can be porosity within the powders. There can be pore structure between powder particles and in the overall component fabricated by powders. Chemical compositions can vary quite a bit, even as starting compositions, and then by the application of high energy and reaction with the atmosphere, that composition can change as well. Certain constituents can evaporate, certain things can react. In addition, depending upon the composition and time temperature phenomena, phase change, crystal structure changes, and consequently properties of the components that are fabricated by 3D printing using some of these powders are all going to change. So of interest is what is the influence of powder attributes on processing. Here's an example of green strength plotted as a function of compaction pressure. One of the key things about learning the influence of powder characteristics is the way they impact processing outcomes. Here, for example, with a traditional powder metallurgy process, die compaction, you have green strength plotted as a function of compaction pressure for two different kinds of powders. One is a reduced oxide iron and the other is a water atomized iron powder. They have completely different powder attributes. You can see that for any given compaction pressure, the green strength is higher for the water atomized powder as opposed to the reduced oxide iron powder. These trends in green strength correlate with increase in the compaction density as a function of increased compaction pressure. So building from that, one thing is by changing shapes and size and other attributes, size distribution and so on, the way powders pack change, the way they flow change, the way they densify or consolidate also changes because the pore structure would be different. Packing behavior affects the initial stage before imposition of let's say a laser energy. Flow behavior affects the way the bed density again changes when the powder is spread across to form a thin layer. In certain binder assisted 3D printing processes, including fused filament fabrication and binder jetting, for instance, the ability to remove binders from uh, the created shape is going to change based on the powder characteristics because the pore structure is going to change. Finally, the melting and sintering behavior are going to change based on the packing density, the particle sizes, number of nearest neighbors, and so on. And when all those aspects of creating the shape get affected, the final properties can be affected as well, starting with density and then from there on going into other aspects, including grain size, phase structure, so on. In addition, the ability to hold dimensions is going to change as well. So that indicates why it's important to understand powder attributes and their influence on outcomes during 3D printing. At the top, you begin to see some lab when I just started out my postdoc that housed some of the best powder characterization facilities that existed. And at the bottom, some microscopy as well. So building up from these 20 years of experience on characterizing powders and their attributes allows us to understand how to link them to the behavior of powders during 3D printing processes. It's also important from the point of view of process control. If you had variations in some of these attributes, such as size distribution and so on, outcomes would change. And so process parameters to influence this outcome are going to drift as well. By understanding these interrelationships between the starting powders and the way you have to print them, you can anticipate variations that might exist because of lot-to-lot variations in powder uh, attributes. And you can set specifications. Of course, the danger of setting specifications is that you only use a certain fraction of the overall powder that the manufacturer produces. And so that can add to the cost. From a R&D perspective, understanding the multiphysics and related thermochemical effects of powder consolidation during 3D printing is some important area of research. Lawrence Livermore National Lab, an important collaborator, has worked to a great extent in leading the overall effort of pooling together information in the context of 3D printing and putting together a professional society in this area. Finally, legal liability protection is an important thing. Right? If you're going to have a lot of drifts in 3D printing outcomes based on these unknown parameters, it is important to protect oneself from failed components, failed systems arising as a result of inaccurate specifications at the beginning of powder attributes.